Okay, so we're going to wrap up this thin film interference lesson once and for all. Yes? We know that if you spill oil on the driveway, you can see that rainbow effect. Or sometimes with bubbles, you see the rainbow effect. We take a close look at a bubble and we zoom in. Closer look, closer look, closer, 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 closer. We're looking at the light that's going to be reflected off the first surface. Hello! And the light reflected off the second surface. First surface and second surface. So,
that really smells good. Whoever has is that a pomegranate, like kiwi or something? Like some odd combination?
So, did we look at these slides? Okay. So, it's fun to play that game, what's in front. But sometimes that just takes too long. So we want to be able to do these problems a lot faster. So to help teach you how to look at the problems in a more efficient way, I want to look at these diagrams here. And basically, this top wave represents the light reflected off the first surface, and this bottom wave represents the light reflected off of the second surface. So I'm talking about the light right here and the light right there. Now, notice the light that is reflected off the second surface over here, it has to travel extra distance before it reunites with the other light, yes? So some of the light is reflected right here, but the other light has to travel all the way down and all the way back up before it reunites with this light over here. So this is a very important distance. And we know the thickness of the thin film is D. And if this is basically happening in an up and down fashion, essentially this extra distance down and back up is equal to 2D. Extra distance down and back up equals 2D. And what we want to do is figure out, like, what does this extra distance have to be if we want these two rays of light to be in sync, to be in phase, to have constructive interference? So let's take a look at these two waves. Now, these two waves are going to be superimposed on top of each other. So imagine if I could pick the lower wave up, place it right on top of the wave right above it. And the question is, if I did that, would we have constructive interference or destructive interference? Are these waves in phase or out of phase? What do you think, Giselle? And if you're not sure, just say so. We'll look at it again. Well, you see right here, there's a crest, and straight up above it, lined up with it, is a crest. And then right down here, there's a trough, and right above it, there's a trough. How it's like lined up if you follow the red lines. So basically, if I put the one on top of the other, would the crest line up with the other crest, or would a crest be lined up with a trough? They're going to line up. So are they in phase or out of phase? In phase. Are we going to have constructive interference or destructive interference? Constructive. Pardon? If they're in phase, that goes hand in hand with being constructively interfering. Now, remember, we're talking about that extra distance that the one light ray has to go down and come back up. So I'm going to move the lower ray, the lower wave, to the left. So that it's going to have to travel a longer distance before it catches up with its friend, the upper ray. Take a look at this. So I just shifted that lower wave to the left. So now it's going to have to travel from here to here, this extra distance, before it catches up with the other wave. So first of all, if I superimpose these waves on top of each other, this wave right here, would end up being put on top of this wave right here. This right here would be end up put on right on top of that right there. Are these waves in phase or out of phase? Say it loud, say it proud, Marissa. Yeah. Okay. Will we have constructive interference or destructive interference if these two waves, where they end up sharing the same space at the same time, if they were superimposed? Destructive. Now this is where it gets important. How much farther did the lower second wave have to travel before it starts sharing the space with the wave above? In terms of wavelengths, Nicole? Half a wavelength. So the distance traveled is a half of the wavelength. And this is the wavelength in the second material. So it's the lambda prime, or if you want to call it lambda 2. From here to here, that right there is a half of a wavelength. That distance right there. So it traveled a half of wavelength on its own. So we know that if the lower wave has to travel an extra distance of a half a wavelength, it's going to be out of phase with the upper one. Let's take a look at the next one here. This time the lower wave has been shifted over to the left even more. The part that will share the same space at the same time is this over here. That is going to be superimposed with this right here. Are those waves in phase or out of phase? Say it loud, say it proud. Rajiv. They're in phase because the crest lines up with the crest. Will we have constructive or destructive interference? Constructive interference. How much farther did that lower wave have to travel before it started interfering with the upper one? One full wavelength. So the extra distance there, the extra distance is one full wavelength. This distance right here. Extra distance is one wavelength. Bravo. You guys with me so far? Okay.
Is this like getting it?
Yes. Be patient.
We shouldn't be copying this down, though, right?
No, you don't have to copy it down. Just pay attention here. Okay. Let's play this game just a couple more times. Okay? In phase or out of phase? Destructive. Extra distance traveled equals 1.5 wavelength. Okay? Everyone on board with that? Joey?
Why is the top one also shifted to the left? So, just because it had the same amount of wavelength?
No. Remember,
that's just a normal. I got it.
that's just where it normally started.
I was looking at it like they were both shifting.
No.
Yeah.
This was the original starting line of both of them, and I just keep shifting the lower one down to the left. As a matter of fact, I'm glad you asked that question because I'm going to go back now and put like a start line right there, and that'll be crystal clear in the future. That's a good point. Yes.
Well, how does it shift the distance that is a factor of half a wavelength?
Then you're not going to get perfect constructive interference, nor are you going to get perfect destructive interference. So basically, you're going to get some kind of interference, but it's going to be like a little bit of both. You know what I mean? It's going to be a little bit off. Okay. So, that's a good question too. So, what the heck? I think we could play this one more time. In phase or out of phase? Let's move this a little way. In phase. Constructive or destructive? How much farther, if this is the start line here, how much farther did the lower wave travel before it started interfering with the upper wave? So, are you starting to see the pattern? If we're going to get constructive interference, the extra distance that the lower wave has to travel always has to be equal to a certain thing. And what is that certain thing? Can anyone answer that question? If we're going to get constructive interference, the lower wave always has to travel a certain thing. Let's go to Michelle in the back.
Would it be n lambda?
Yeah. And n is going to be what?
Any number of the maximum. It would just be the weight length of the number of
Exactly. Is it a whole number or like fractions or?
the whole number.
Yeah, it's any whole number. It's going to be any whole number. N lambda. Any whole number of lambda. It's going to either be 1 lambda, 2 lambda, 3 lambda. You with me, people? Okay, so now we go back to the problem at hand. Okay? Now, you know how sometimes the light goes through a phase change? And that's what makes the game What's in Front so much fun to play? For now, let's just forget about the phase change. Let's keep this really nice and simple. Let's say that these indices are such that the reflected light right here and the reflected light right here, the one right there and right there, maybe I could, the reflected light right there and the reflected light right there, neither of them go through a phase change. Keeping this nice and simple. So, my question to you is, if we want these two light rays, this one and this one, to have constructive interference, the extra distance that this light wave has to travel, which is down and back, that's the extra distance that this guy here has to travel before it reunites with that guy right there. The extra distance down and back which equals down and back is going to be equal to 2d, twice the distance. Now, I know what you're saying. Isn't there a little triangle there? Isn't it the hypotenuse? But remember, we're really considering the simplest case where the light is going straight in, straight down, and straight back up. So it's basically 2d. What do we want that extra distance to be equal to if these guys over here are going to end up in phase with constructive interference? What does this have to be equal to, the extra distance, in order that those two emerging light rays are in sync, in phase, so you get constructive interference? 1, 2, 3, 4, 5, 6, 7. The rest of you, are you just being shy? Or you're really not sure? I'm not going to call on anyone who doesn't have their hands raised. So just be truthful and raise it if you think you know what that blank is.
Why is the blank so blue?
I don't know. Okay. Thank you for those of you who have your hands up. I'm pretty sure you probably know. But let's go back and let's talk about this again. Okay? This extra distance traveled folks, if we go back over here, right now these two waves are in phase with each other, yes? What's the extra distance traveled by the lower one? 0. Because they're both starting at the same point. They're both starting right here. This one here, if this is the starting line right here, the lower wave had to travel an extra distance first before it joined up with the other one. How far did it have to travel? A half a wavelength. Did that lead to constructive interference? No, that led to destructive. See how they're out of phase? Look, here's the starting line. The extra distance traveled by the lower wave before it joined up with the upper wave was 1 wavelength. Did that give us constructive interference? Yes, it did. Okay? So, what was the deal? 1.5? Did that give us constructive interference? No, destructive. If the extra distance is 2 wavelengths, did that give us constructive interference? Yes. So when we come over here, the extra distance, I know it's complicated now because it's not along a straight line, but this right here is the extra distance. Because look, here comes the light, oh, here comes the light. And then some, right then and there, boom, reflects up. But some has to travel extra distance down and back up before it reunites. So the extra distance now is down and back up. 2D. What does that extra distance down and back up have to be equal to such that you get constructive interference? Jamie? It will definitely work if the extra distance down and back up is exactly 1 wavelength. Whoa. Or, what else could it be? Krista? What other extra distance gave us constructive interference? Let's go back and look. Okay. Half a wavelength extra distance? Did that give us constructive? No. 1 full wavelength? Did that give us constructive? Yes. And that's what Jamie said. Extra distance, 1.5 wavelength? Did that give us constructive interference? No. 2 wavelength? Did that give us constructive interference? Yes. So what's another value of the extra distance that'll give constructive interference? See? 2 wavelengths. Or, do you want to take a guess what the next one is? 3 wavelengths. Or 4 wavelengths. So the extra distance, 2D, has to be a whole number of wavelengths so that the 2 emerging rays are in sync with each other. But now what makes this even more tricky, what is the extra distance equal to? Twice the thickness of the film, because that light has to go down and back up. So since the light has to go down and back up, the extra distance traveled is 2D. So if we go and solve this now, we know that 2D can be equal to 1 lambda. Well, if I solve it for that case, what thickness do we want the middle material to be? Jeremy?
Half lambda.
Half a lambda. 1/2 times lambda. So that there will give us hello constructive interference. The next case. What if the extra distance, 2 times d, is equal to 2 wavelengths? And I should put primes on these because it's the wavelength in that second material. Then, what does the distance thickness have to be? Henna? Solving that for d?
The
Or it could be 3 lambda. The extra distance could be 3 lambda. So, what could the thickness be? Austin? Yeah. Or you know what I'm going to say? I'm going to say 3/2 lambda, which is 1.5 lambda. Excellent. And we could keep playing that game. But these are the thicknesses that would give us perfect constructive interference between the first reflection and the second reflection. You follow me, people? Take a quick 30-second break, and then let's look at another example. All right, we're back. Now, let's say there's a phase change at the first surface. In that last problem that we just looked at, there was no phase change at either boundary. But you know, sometimes there is a phase change. So let's take a look at that. Boom, boom. Let's say the light coming down, right here, when it reflects, let's say it goes through a phase change. So I'm going to say here PC, where PC stands for phase change. But let's say there isn't a phase change with the other light, the light that goes down here and reflects. Let's say right there, there's no phase change. No phase change. So there's only a phase change at one of the two boundaries. Now see if you can follow the logic here, people. Remember before, if the extra distance down and back, if the extra distance down and back up, which is always equal to 2 times the thickness there. Remember last time, if it was equal to 1 wavelength, what kind of interference did we get before in the last example, Ryan? You would get constructive interference, yes? But would you get constructive interference this time because the top wave had a phase change? Maybe we should go back and take a look. Let's go all the way back. Boom, 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 boom. Here we have the 2 waves. Let me erase this work here. Wah, wah. Let's give the top wave a phase change. I'm going to flip it. So instead of being there, it's like this now. So I ignore the fact that I made it thicker. I just want it to stand out. So we have that wave on top, the wave on bottom. Right now, are they in phase or out of phase? what kind of interference would we have? Okay, let's go to the next setup. Okay. Ooh, I forgot to erase. Okay. Okay. In phase or out of phase? I flipped the top wave. In phase. Constructive or destructive? What's the extra distance that the lower wave had to travel? Half of a wavelength. So the extra distance traveled up and back is equal to half of a wavelength. Yes? What about the next one? Erase. Phase change on the upper one. I think I might have screwed it up, but good enough. Anyway, okay. In phase or out of phase? Out of phase. Constructive or destructive? What's the extra distance that the lower one had to travel? So, when the one wave here goes through a phase change, things change, yes? So let's go back to the problem at hand here. Where are we? Come on. Come on. There we go. The top wave went through a phase change. Jeffrey, come on. Top wave went through a phase change. If we want constructive interference, people, if we want constructive interference, then what does that extra distance down and back have to be equal to now? Austin? You guys see that? The extra distance now, down and back, would have to equal a half of the wavelength. Or, what else could it be equal to for there to be constructive interference? Jeffrey? For constructive. 1 1/2. Or 2 1/2 wavelengths. Why the half this time? Dave? What's happening this time that didn't happen before? Phase change on one of the surfaces. So now we have to solve each of these for D, the thickness. So what does the thickness here have to be? What is it? 1/4 lambda prime. Or, what's the thickness? 3/4, right? Or, what's the thickness? What is that? 5. 2 1/2 divided by 2. So that would be 1, so that would be 5/4. Somebody said it too, I heard it. Anytime you're given a problem with thin film interference, and they ask you, like, what thickness will give you constructive or destructive, I'm going to tell you right now, the answer for the skinniest non-zero thickness is always going to be equal to either a half a wavelength, like we got over here, half a wavelength, or a quarter of the wavelength. It just depends on what's happening. So, last but not least, what if there's a phase change at both surfaces. Oh my goodness. This is getting really complicated now. The light that hits here goes through a phase change. The light that goes into there and comes up right there goes through a phase change. Well, if you think about it, if they both go through a phase change, once again, what would we want the extra distance down and back up to be for constructive interference? One whole wavelength, exactly. Or, exactly. If they both go through phase changes, the problem is just like what? This one here, when neither of them go through phase changes. If they both flip, it's the same thing, you know what I mean? So basically, same answers as when no phase changes. So of course, practice helps. Let's look at a typical AP problem pertaining to this stuff. Don't copy down the problem. Let's just read it. Okay, try to get a grip. So you can watch me now. Maybe you can try to do this by yourself at home. Suppose that monochromatic light, one colored light, with this frequency right here, is traveling through the air when it reaches a thin film. Notice it goes from n equals 1 to n equals 1.2 to n equals 1.5. The question is, what's the minimum non-zero thickness of that center film right here? What's the smallest thickness from there to there that will give, for part A, constructive interference? Well, first thing we have to do is check out to see, are there phase changes here or not? So, when the light comes down and refracts and goes in here, the light that reflects up off that first surface, does it go through a phase change? Does this light right here go through a phase change? And how would you know? Is it going fast to slow or slow to fast? Fast to slow. And when a wave goes from fast to slow, does the reflected piece go through a phase change? Yes. So there is a phase change right here. What about at the second surface? When the light hits here, some of it continues on through. And some of it reflects up. Would this light right there go through a phase change? Yes. Because again, it's going from 1.2 to 1.5. It's slowing down even more. So it's going from slow to slower. So this here is going to go through a phase change. So since there is a phase change at both surfaces, how much do we want the extra distance down and back up to be, so that the light that comes off the first surface and the light that comes off the second surface are in phase, constructive interference? How much do we want that extra distance down and back up to be? So, extra distance down and back up equals 2D equals, how much do we want it to be, Michelle? 1 full wavelength. That's what it would need to be in this case. So, or what else could it be, by the way, Michelle? Exactly. You got it. So if I solve this for the thickness D, if I set those equal to each other, what would D have to be equal to? Great. Now, we still have to figure out what lambda prime is. It's been a while since we looked at that. We're just about out of time, so see if you can follow me on this. We're not going to crunch it, but I'll just show you the way. You see how they gave you the frequency right here? Well, if you use the wave equation, velocity equals frequency times wavelength, the frequency was given, what would this velocity be up there in air? Roger? 3 times 10 to the 8 meters per second. So what can we solve this for? Lambda, the wavelength out here in the air, yes? And then remember we derived that formula? Lambda in the new material is equal to lambda originally divided by the n in the second material. So if we put the lambda that we got here, right into there, we can get lambda prime, and then come back over here, and we can solve for the thickness. By the way, in part B, they want to know what is the skinniest thickness, non-zero thickness, if you wanted perfect destructive interference. Since they both go through a phase change, watch my key, because I'm not asking for the answer yet. If they both go through a phase change, if we wanted destructive interference, what would we want this extra distance down and up to be? Half lambda. Therefore, what would the thickness have to be? 1/4 of lambda prime.
Can it also be a 3/4?
Yes. But that wouldn't be the skinniest one.
Oh.